Complex numbers 1. Complex numbers, the Argand diagram, and modulus. Part 1, definitions. When the formula x equals minus b plus minus the square root of b squared minus 4ac divided by 2a is used to solve the quadratic equation a squared plus bx plus c is equal to 0, it quite often happens that we get the square root of a negative number. So basically the number underneath the square root is negative. In this case, we can always say that the quadratic equation has no real roots, because there is no real number whose square is a negative number. As we know, if p is an element of the real number set, then p squared is greater or equal to 0. Alternatively, we can extend the definition of what we call numbers to include the square roots of negative numbers. Then it will be possible to say that all quadratic equations have roots. This is the more forward-looking approach, as it gives a new collection of numbers which have many applications in maths and in real life. Some of these will be seen later in this chapter. To extend our system of numbers, it is only necessary to introduce one new concept, that of the square root of minus 1. This is denoted by the letter I, and is referred to as the imaginary unit, with reference to the original idea that such a number doesn't exist and hence is imaginary. So if I is equal to the square root of minus 1, if we square both sides, then the root and the squared cancel, and we're left with I squared is equal to minus 1. This is the preferred definition of the imaginary unit. We can now write the square root of any negative number in terms of I. For example, the square root of 16 is the square root of 16 multiplied by minus 1. And that's broken down as to square root 16 multiplied by square root of minus 1. The square root of 16 is 4. The square root of minus 1 is I. So actually the square root of minus 16 is 4i. Any number in the form ki, where k is an element of the real number set, is called an imaginary number. A complex number is a number that involves this new imaginary unit. Specifically, a complex number, z, is a number in the form of z equals a plus bi. This capital letter C represents complex numbers, includes all real numbers and all imaginary numbers. But most complex numbers are neither real numbers nor imaginary numbers. So complex number C. So C is equal to a plus bi, where a and b are elements of the real number set, and I squared is equal to minus 1. If z is equal to a plus bi, then a is equal to the real part with z in brackets, and the b is equal to the imaginary part, again with z in brackets. The Venn diagram below shows the relationships between the different number systems on our course. The set of natural numbers n is a subset of the set of integers z. So the natural numbers are a subset of z, the integers, which in turn is a subset of the set of rational numbers q. This set is a subset of the real numbers or, which is then a subset of the set of complex numbers C. Another subset of C, which is disjoint from or, is the set of imaginary numbers written as Im, which contains purely imaginary numbers, like minus 7i, for example. However, most complex numbers, for example 2 minus 3i, belong to neither or nor Im. They are simply complex numbers. So for example, the number 2 minus 3i lies outside of the real number set and outside of the imaginary number set, and it lies inside the complex number set. The Argand diagram. Complex numbers may be represented graphically on a diagram called an Argand diagram, named after the Swiss mathematician Jean-Robert Argand, who proposed the theory in 1806. An Argand diagram looks like an ordinary x, y, or Cartesian plane. However, the x-axis is called the real axis, or e, and the y-axis is called the imaginary axis, im. So the x-axis, the horizontal line, is now the real axis. And the imaginary axis was once the y-axis, is now the imaginary axis, labelled IM. The complex number z equals a plus bi is represented by the point AB on an Argand diagram. So this is the point z, which is the complex number a plus bi, and the a part is the real part, and the b part is the imaginary part. For example, the complex number 3 plus 2i, 8, and minus 2i can be represented on the Argand diagram by the points 3, 2, 8, 0, and 0, minus 2 respectively. Modulus of a complex number. If z is equal to a plus bi, it is represented by the point AB on an Argand diagram. The modulus of z, written as z with a line either side, and we are used to seeing this notation as the distance or length, is the distance from the origin O, which is 0 plus 0i or 0, 0, to the point representing z on the Argand diagram. So modulus represents the distance to the origin. By Pythagoras' theorem on the triangle shown, so here's our right angle triangle, z squared is equal to a squared plus b squared, so z being the hypotenuse is equal to a squared plus b squared. So the modulus of z, we basically just bring our squared over the equal sign and becomes square root. So to get the modulus of a complex number, we square root the a, which is the real part squared, plus the b, which is the imaginary part squared. The greater the modulus of a complex number, the further it is from the origin. The Argand diagram opposite shows the four complex numbers z1, z2, z3, and z4. So we have z1 is on the imaginary axis, z2, z3 is on the real axis, and z4. Part 1. If one of these is 3 plus 3i, identify which one. So 3 plus 3i is 3, 3 as a coordinate. Thus, z2 is equal to 3 plus 3i. So we go across to 3 on the real axis and go up to 3 on the imaginary axis. And the point at which they meet is z2. The complex number is z2. 3 plus 3i. Part 2. Write down the other complex numbers in the form a plus bi. So z1 is the coordinate 0, 4, which is 0 plus 4i, which is just equal to 4i. So we don't have any real part. So z1 we see is on the imaginary axis. So it has a real value of 0 and an imaginary value of 4. So it's just 4i. z3 is the coordinate minus 2, 0, which is minus 2 plus 0i. So we have no imaginary part. So it's just minus 2. So we see on the real axis, z3 lies on the real axis. So it has an imaginary part of 0 and a real part of minus 2. So it's just minus 2. And z4 is the coordinate minus 3, 2, which is minus 3 plus 2i. So minus 3 on the real axis, 2 on the imaginary axis. So we get the point z4 at minus 3 plus 2i. Part 3. Determine which of the four complex numbers is the furthest from the origin. So what we're going to do is use our modulus formula, which is the square root of a squared plus b squared, where a is the real part and b is the imaginary part. So the modulus, which is represented by these two lines here, which represents distance or length. So in complex numbers, the modulus is the distance from the complex number to the origin which is in the center, 0, 0. So the modulus of z1 is going to be the square root of 0 squared plus 4 squared, which is the square root of 16, which is 4. The modulus of z2 will be the square root of 3 squared plus 3 squared, which is the square root of 18. The modulus of z3 is the square root of minus 2 squared plus 0 squared, which is the square root of 4, which is 2. And the modulus of z4 is the square root of minus 3 squared plus 2 squared, which is equal to root 13. As z2 is the complex number with the greatest modulus, root 18, it is the one furthest from the origin. Argand diagram and modulus. The complex number z equals a plus bi is represented by the point a comma b on an Argand diagram. The modulus z equals a plus bi, which is written as this, which is z with a line either side, which is the exact same notation as length or distance, is given by the modulus of z is equal to the square root of a squared plus b squared, and represents the distance from the origin to the point AB. At this stage, it is important to realise that an Argand diagram only looks like an ordinary xy plane from coordinate geometry. As we will see, points on the Argand diagram can be added, subtracted, multiplied and divided in a way that is not possible for points on an xy plane. As well as being necessary in the solution of many equations, complex numbers are used in many real-life contexts, particularly those where two quantities vary simultaneously. Some examples are radio waves, mobile phone signals, and dealing with current, resistance and voltage in alternating currents.